All right, now we start chapter 3, which is titled Composition of Substances in Solutions. But what you should be really thinking about with chapter 3 and chapter 4 to follow is this is where we start to get into the math gauntlet of general chemistry, right? 3, 4, and to a lesser extent 5 is really when you're going to be putting your math skills to the test in the context of chemistry. So ideas from chapter 1, for example, dimensional analysis, make sure you're comfortable with how to use that, because even in this video today, we're going to continue to use those types of conversion factors. Okay? And the big question we're focused on here in chapter 3 is how do we calculate what molecules are made of, right? And then do math with their molecular compositions, right? You see their composition of substances, that's what we'll start with, and then solutions later on in 3.3. So we've got 4 subchapters in chapter 3, so we will have 4 videos, and this one will cover 3.1, formula, mass, and the mole concept, and then 3 videos to follow. Okay? The first 2, 3.1 and 3.2, will be a little bit on the longer side, and then we wrap up with 3.3, molarity, where we get a new conversion factor for solutions, and then other units in the end for 3.4, which will be the smallest subchapter, making sure that we continue to use dimensional analysis throughout. So formula, mass, and the mole concept, addressing that question up top, what do we do with chemical formulas? Because in chapter 2, we learned how to put those formulas together in molecules and ionic compounds, right? And we learned about atomic mass units, right? And using atomic mass on the periodic table. We used it, for example, to calculate the number of neutrons. And understanding those atomic masses and the information that they give us, as you'll see, led to a lot of important discoveries on top of what we already saw from chapter 2. So what is formula mass, right? It is the sum of the average atomic masses of all the atoms in the formula. Okay, so an atomic mass is the mass of one atom. A formula mass is the mass of everything that's in a compound. Okay, so it's kind of just an extension of that idea. We can still keep the units the same and think about it as being in atomic mass units. We are now just thinking about it as, for example, on this slide, a molecule. So we take everything that's in the molecule, add up their atomic masses, and that is the formula mass of a covalent compound. We can also call that a molecular mass. So you can see those two terms used interchangeably, right? Formula mass, molecular mass, because we're dealing specifically with molecules. So how do we do that? Right? If we look at this slide here, we're trying to calculate the mass of chloroform, right? If you're asked to calculate the formula mass. Well, first we have to look at the formula. Right? At this level, I don't expect you to know, right, chloroform, exactly what that molecular formula is. So I look down here at the molecular formula. It's CHCl3. And that formula gives me important information. It gives me the types of atoms that are present in the molecule and the quantity. So I have 1 carbon, 1 hydrogen, and 3 chlorines. So I break them apart, 1 carbon, 1 hydrogen, 3 chlorines. I get their average atomic mass from the periodic table. Okay, so using that value of A, you've got to have your periodic table. And then I multiply them by one another. So carbon and hydrogen, that's easy. Chlorine, 3 times 35.45 gives me 106.35. Add all 3 together, and that gives me the molecular mass. So for every molecule of chloroform, it has an average atomic mass of 119.37 AMU, atomic mass units. And this is something for the chapters that follow, right? We've got 7 more chapters to go, 3 through 9. You will continue to have to calculate formula mass. So this is an important idea. You need to know how to quickly calculate that. So here's an example that you can practice, right? Calculating the formula mass of aspirin. And again, the formula will be provided to you. Right? Anything that's not simple nomenclature. If it's something we learned how to do in chapter 2, like take dinitrogen tetroxide, N2O4, right? That I would expect you to know. That means N2O4. Right, but any common names like chloroform or aspirin, I will give you the formula. So I recommend you pause the video here and practice calculating the formula mass of aspirin, knowing that that's C9H8O4. So the method is to break them apart: carbon, of which you have 9, hydrogen, of which you have 8, oxygen 4. Pull their atomic masses off of the periodic table. So you'll have to look it up for carbon, hydrogen, and oxygen. Then multiply their quantity times their atomic mass and add everything together. If you do that correctly, you should get an answer of 180.15 AMU. If this is something you're struggling to see the method and exactly what's going on, because it is shown for each one in this video how to do it, then let me know. That's something we can discuss in lecture or in review. So these chloroform and aspirin, these are molecules. We can call that a molecular mass. But what about ionic compounds, where we have a metal and a non-metal? We know that ionic compounds from chapter 2, right? We know how to name them. We know that it's a cation and an anion coming together, right? Electrostatically attracted to one another. They're neutral overall, right? So they only come together in one ratio. But ionic compounds don't exist as discrete units, right? We covered this before. They don't float around just like molecules. So we don't call it a molecular mass if we're dealing with an ionic compound. Okay? We just think about it as a formula mass. But as long as you keep that in mind, right, it's calculated the same way. It's just a different name. Formula mass for ionic compounds, molecular mass for covalent compounds or molecules. But after that, if we take sodium chloride, for example, it's NaCl, so 1 Na, 1 Cl. Add the two together, 58.44. If you had something like, CaCl2, for example, calcium chloride, then you would need 2 times 35.45 because there's 2 chlorines. Okay? But as you see, it's calculated the same way. Know how to calculate formula mass or molecular mass. Okay. Now, everything we've talked about so far in this video is thinking about individual molecules or ionic compounds. But if we're thinking about working in the lab, for example, we're working in the macroscopic realm of chemistry where we can actually hold things with our hands and see them with the unaided eye. So we need some sort of conversion factor to bring us between these realms. And this is the idea of the mole, okay? Which is not the mole, the animal, which is in the top right corner here. It comes from Latin for bulk. And this is a concept you've probably heard of, having taken chemistry in the past. All right, we can't measure atomic mass units directly. We don't have a scale that can measure the individual AMU, right? So we use mole as kind of an aid to help us calculate the atoms in a whole quantity of something that we can measure in the lab, for example. Yeah. So what is the mole? It is an amount of something. Okay. So if you say that a dozen, you get a dozen donuts or a dozen beverages, right? That means 12. Mole is the same idea, okay? And the number comes from Avogadro's number, which we have on the next slide. Okay. Where did the idea come from, right? The definition of a mole, it is the number of atoms in a sample of pure carbon-12 that weighs 12 grams. Okay. And you're going to see this is really useful because it allows mole and AMU to be directly related to one another. And that gives us a link between the mass of the sample and the number of atoms, molecules, or ions, depending on what we're dealing with specifically. That's the key to relate those two worlds, right? What we're dealing with on the individual atomic scale and what we can measure in the lab and deal with in the macroscopic realm. Okay. So I alluded to it before. Here we go on slide 10. Right? If a dozen is 12, a mole is 6.02214,179 times 10 to the 23rd. Okay? You don't have to know that whole number, but I do expect you to know the first 4 significant figures. Okay, so you absolutely 100% need to memorize Avogadro's number, right here. It's represented by the symbol N sub A equals 6.022 times 10 to the 23rd. And that would be units per mole, right? Anything you want. 6.022 times 10 to the 23rd atoms in a mole of atoms. 6.022 times 10 to the 23rd molecules in a mole of molecules. All right. So it's a quantity, right? So what that means, if I'm measuring out the quantity, depending on what I'm measuring, it's going to have different masses. And that's what the last bullet point here is talking about, okay? The masses of 1 mole of different elements will have different masses because the mole is the quantity, right? If I take a dozen, water bottles compared to a dozen, I don't know, bricks, right? The bricks are going to have a different mass, even though there's 12 of each. Okay. So here, if I take exactly a mole of these different atoms, they have different masses, right? 65.4 grams of zinc, 12 grams of copper, 207 grams of lead down here, and you see other examples up there. In the molecules, the number of molecules for these guys is the same. Okay, so all of those represent exactly 1 mole. It has the same amount, the same number of atoms in this case, as the others. So 1 mole of something has the same quantity as 1 mole of something else. But as you see here, the masses are very different because the atoms that make these things up have different masses themselves. Okay, so atoms and molecules have different masses. I hope this is making sense. Okay. And you might notice something notable about those numbers, right? They correspond to the atomic masses on the periodic table, which we're getting to. Okay. So as you can see, 6.022 times 10 to the 23rd, right? 6.022 and then 20 more zeros after that. It is a crazy big number, right? A single mole, right? If you took 1 mole of red blood cells, that's more than every human being in the world has in them, which is crazy to think about because you yourself have 20 to 30 trillion red blood cells in just your body, multiplied by every human on Earth, and it's still not a mole. And if you took a mole of basketballs, it would be the size of the Earth. But we need that huge number to make the connection between those crazy tiny atoms that we talked about in chapter 1 and the macroscopic domain where we can actually measure things out. And that brings us to the idea of molar mass. Okay, so this is tying back to what I referenced before and which is at the bottom of the slide here, right? The units for mole and atomic mass unit are both based on the same reference, carbon-12, which is incredibly useful. And then all other elements are based on that same reference. So we get the same kind of relationship. And that relationship is the fact that the molar mass of a compound, which has the units of grams per mole, is equal to the formula mass in atomic mass units, which we just talked about how to calculate. Okay. So that's what this middle bullet point is saying. Molar mass of any substance is numerically equivalent to its atomic or formula mass in AMU. Difference just being, right, if it's an atom or a molecule or an ionic compound. So what is the molar mass of an element or a compound? It is the mass in grams of 1 mole of that substance. Okay, so jumping back to this slide, the mass in grams of 1 mole. So the units, jumped ahead there, are grams per mole. So the units are grams in 1 mole of that substance. And as I just mentioned, 30 seconds ago, that is equivalent to the formula mass in atomic mass units, which is why we started this section by figuring out how to calculate formula mass. Because if you can calculate the atomic mass, the molar mass is the exact same number. We just changed the units, atomic mass versus grams per mole. And they have the same number, but remember that they are very different scales, right? 12 AMU, so it's 12 atomic mass units in 1 carbon atom. It's 12 grams, So that's something you can actually measure on a scale in the lab in exactly 1 mole of carbon. Okay. Keeping in mind, of course, that 1 mole is very different for different things, right? Here we see 1 mole of some solids. Mole can also be a liquid or even a gas, right? But remember, mole is a quantity. It can look different, as we see on this slide, and it can have very different masses. Okay. So now, keeping that in mind, what we've covered so far, we can get to the math part of this chapter that I alluded to before. Because those relationships between formula mass, the mole, and Avogadro's number, right, are huge. They tie in a lot of things in chemistry together. Okay? We could do all sorts of different calculations and compute different quantities relating to the composition of these different substances. And what we are covering in this section, 3.2 and 3.3, it's all these same types of calculations. Fundamental concept moving forward. You have to know how to do this math as we proceed in general chemistry. Okay, so we've got mass, chemical composition, and moles. If we know 2 of them, we could typically calculate the third. And they're related in this triangle, which I pulled from outside of your textbook. Okay, some people like this slide, some people don't, right? It shows you how to do all the different calculations to relate the mass of an element, the number of moles of an element, and the number of atoms of an element. And we're going to look at a lot of these calculations for the rest of section 3.1 here. And so if you like this slide, use it. If you don't have to consult it, because we're going to see how to do these calculations. And then as long as you're using dimensional analysis to track your units and putting the numbers in the right places, you'll be all right. But that's just an extra resource for you to have if you want it. So now, as I said, let's look at the math, right? How do we do these things? A bunch of example problems. Okay. According to the nutritional guidelines from the U.S. Department of Agriculture, the estimated average requirement for dietary potassium is 4.7 grams, right? If you are working on this on a test, for example, you don't care about most of that sentence. The only thing you need to pull out is 4.7 grams of potassium and know that potassium is K on the periodic table. And it asks, what's the estimated average requirement for potassium in moles? Okay, so I was given grams of potassium, right, mass, and I need to find moles. So how do I relate those two? Well, I'm starting with grams. I want grams to go away, so it was in the numerator and now the denominator. How do I relate grams to moles? Well, I can use the molar mass of potassium, right? So I look at potassium on the periodic table, right? It's got an average molar mass of 39.10. That's grams in 1 mole of potassium. Right? It's not moles in 1 gram. So 39 goes down here, 39.1 grams in 1 mole. And then I take 4.7 divided by 39.1 with significant figures, I get 0.12 moles of potassium. Yep. It's a unit conversion similar to what we saw in chapter 1. Now just continuing to use dimensional analysis to calculate different quantities. So there we're relating grams to moles. Okay. What about going this way on slide 19? Okay. Liter of air has 9.2 times 10 to the negative 4th moles of argon. And then we're asked to calculate the mass of argon in a liter of air. So this is the part of the video, right? They're all broken down in the slides, but you're going to want to pause for each of these and try to find the answer. So here, right, I've got 9.2 times 10 to the negative 4th moles of argon. Okay. I'm asked to convert that to mass. And we just saw I can convert grams to moles. Right? But how do I do it? Okay. I have moles and I want to convert to grams. So if I set my conversion factor up right, I want moles to go away. So it started in the numerator, now it's in the denominator, and I want to convert it to grams. I can do that. I can always relate grams to moles. Okay? Now I just have to put my numbers in the right place. Okay? So this was 9.2 times 10 to the negative fourth. If you haven't ever seen that E before, it represents times 10 to. And then I can relate grams to moles. That's no problem, but I have to do it for argon specifically. So I go to argon on the periodic table. I look up its molar mass, okay, 39.95 grams per mole. Now, right, moles cancels out because it's on the top and the bottom. I'm left with grams. I multiply 9.2 times 10 to the negative fourth, multiplied by 39.95, and that gives me my final answer, which is shown on the next slide here. 0.037 grams of argon. Now I've related moles to grams. I can go grams to moles. I can do moles to grams. No big deal. What about a problem like this? This tells me how many, or asks me rather, not tells me, you're going to tell the answer. How many copper atoms are in 5 grams of copper wire? Now I just said you can always go grams to moles or moles to grams. What you should commit to memory now is you can never go directly from grams to atoms or atoms to grams. You cannot do that. You always have to make a pit stop at moles. Or another way I've taught it in the past is you have to go over the molehill to go from grams to atoms or atoms to grams. You always have to convert to moles first. Okay, so this is a two-step conversion. I have a mass of copper atoms. I need to divide by the molar mass first to go to moles of copper atoms, and then multiply by Avogadro's number. That's 6.022 times 10 to the 23rd to get the number of carbon atoms. So I recommend that you try that one on your own. I will upload a separate video showing how to solve this problem on paper. Okay, a little cleaner than these annotations. How about another one here? Example 3.6. Our bodies synthesize protein from amino acids. One of these amino acids is glycine, which has the molecular formula C2H5O2N. Okay. How many moles of glycine are contained in 28.35 grams of glycine? Okay, this is a good question, because we know we can go from grams to moles, which is what this question is asking us to do. Go from grams to moles. I just said we can always do that in a one-step conversion. But that's using a formula mass. Right? Previously, when we were doing atoms for argon and potassium, we could look them up on the periodic table. But glycine isn't on the periodic table, right? Because it's a periodic table of elements, and glycine is a molecule. So before I can convert from grams to moles, I need to calculate the molecular mass of glycine using this formula up here. 2 carbons, 5 hydrogens, 2 oxygens, and a nitrogen, multiplied by their respective atomic mass. So first, and I recommend you pause the video and do this, you calculate the the formula mass of glycine. Then when you have that, that tells you how many grams are in 1 mole. Then you take that 28.35, divide by that new molar mass, and that'll give you the final answer in moles of glycine. I recommend you pause the video and try that. And then after you get an answer, you can check yourself with this slide right here. Final answer of 0.378 moles of glycine using the correctly calculated molecular mass of 75.07 grams per mole. And always double check that you're putting your units in the right place. Okay? Grams you start with, so you need 75 grams on the bottom. That's why I recommend you use dimensional analysis to track your units and make sure you're doing your math the right way. Okay? Because if you multiplied by 75 in this case, you would not get the right answer. Another one, okay, example 3.7. This tells us vitamin C is a covalent compound with the molecular formula C6H8O6. Okay, recommended daily dietary allowance of vitamin C for children aged 4 to 8 years is 1.42 times 10 to the negative fourth moles. Again, test-taking strategy. Don't worry about a big word problem. Pull out the information that you need. Right? You need that formula, C6H8O6. You need this amount, 1.42 times 10 to the negative fourth moles. Great. That's all I need. I can ignore the rest. What is the mass in grams? That's what it's asking me to solve for. So can I convert from moles to grams? I can, right? We said we can always go from grams to moles or moles to grams. And this question is even easier because it tells me the molar mass for vitamin C, 176.124. So that's great. Okay. I have what I'm starting with, right? 1.42 times 10 to the negative fourth moles of vitamin C. I set up my conversion factor. I know I want moles to go away, and I'm converting to grams, right? Because I know I want those to disappear and get my final answer like it asked me to do in grams. And then it's just a matter of making sure I put the number in the right place, right? It's 176 grams in 1 mole. Right? So I can't put the 176 down here because that would be 176 moles in 1 gram, which doesn't make sense because a mole is huge. So I do 176.124 right, in 1 mole. So this question is asking me to do multiplication to get my final answer because those two are both on the top. And then again, right, the final answer is shown with sig figs 0.0250 grams of vitamin C. Or you could do it in scientific notation, 2.50 times 10 to the negative second grams of vitamin C. You should definitely try these on your own for practice if you're not understanding what's going on, and you'll have more on your sapling. One last example, right? A big one to tie all these ideas together. Okay. Packet of sweetener contains 40 milligrams of saccharin, and we do need that formula, C7H5NO3S. Which has the structural formula shown below. How many carbon atoms are in the sample? Okay, so this is another one that I will upload a separate video for because it's a multi-step conversion. But before you watch that video, I do recommend you try this on your own. You need to pay attention to the fact that it's 40 milligrams, not grams, which is significant. You'll need to calculate a molecular mass for saccharin, and then think about the fact that it's not asking just for molecules of saccharin, but rather the fact that it's asking for carbon atoms that are in there, which is notable as well. The approach is also shown on this slide, 27. Okay. So I do recommend you try it on your own. I'll have a separate video showing the total approach, right, explaining step by step what's going on. And I've mentioned it as we've gone through this video, right? But these are all examples of questions you could see on a test, right? So you should know how to do these. Practice from the slide, practice from the book, practice from sapling. You have to know how to do all these types of conversions to relate grams, to relate molecules, to relate atoms, to relate moles. Right? Any which way, like you saw with that triangle several slides ago. You can relate all of these quantities. It's just a matter of tracking the units and doing the right types of conversions. So I encourage you to continue with that practice, and we'll pick up with these ideas in 3.2 when we learn about calculating empirical and molecular formulas.